Hi everyone, welcome back to yet another exciting tutorial. And in this tutorial we are going to build a decentralized exchange like Uniswap, and the latest functionality Uniswap v4 functionalities we are going to add, and we are going to build it from scratch. We will test it, we will build it the main smart contract, we will test it, and we will deploy it on rootstock blockchain. So what is rootstock is Bitcoin's sidechain, and you can think it as Bitcoin's DeFi layer. So if you want to learn more about, you can, here we are on rootstock.io. If you want to learn more about rootstock, you can go here, and as a developer you can go through here on documentation, and you can explore the documentation. They also have activator program on live right now. Live, you can, here you can contribute to code and earn some code and other contributions and earn some rewards. So you can see all the tools. Rootstock, since rootstock is EVM compatible, you can use the same, same tools as you use on Ethereum development, and you can, using the same tools, you can build decentralized applications on rootstock network. So let's go ahead. The prerequisites of this video is to make sure you have installed um, Foundry in your system. Also make you must have at least basic understanding of DeFi and smart contracts. So this is not beginner friendly tutorial, let me be honest. This is little advanced tutorial, and if you didn't install Foundry, you can go to getfoundry.sh introduction/installation and install the Foundry according to your system. Let's go back here, and let make sure you also install MetaMask, and added these rootstock testnet and mainnet to your MetaMask wallet. And also make sure you have faucet. To get faucets, just copy this address and go to faucet.rootstock.io and paste the address here, and let's say check here. Indeed, I am not robot. Let me refresh this. Now you can copy the address, check I'm not robot, and get test RBTC, and you will get faucets. And let's go ahead and let me tell you the features of our smart contract. We are going to implement AMM. What are the AMM? And we are also going to implement the constant formula, which is mostly you might have know what is the constant formula. Is x multiplied by x multiply y is equal to k. We also are going to add liquidity provision to add and remove liquidity from liquidity pools. We will also going to implement token swap functionalities, and price oracles, fee collection, and the most important, we are going to add reentrancy protection. Contract will be ownable, and we are also going to build a mock token for the text testing purposes. So you can see here I got some test RBTC. So without further ado, let's jump right into coding and start building our smart contract. For that, let's create a new folder. Let's name it RSK DEX and open it in our VS Code. There we go. And yes, I do trust. Let's make it, let's expand this and open up our terminal, and we are going to use Foundry. So let's initialize the Foundry project by running this command for unit. And since we are dealing with DEX, we will need a lot of libraries, external libraries. So we are going to use OpenZeppelin for this smart contract, OpenZeppelin smart contract library. So let's install OpenZeppelin by running this command for install OpenZeppelin slash OpenZeppelin dash contracts, and let's hit enter. And let's see OpenZeppelin is installing, and while it is installing, let's go ahead and delete this counter.t.sol because we are going to build everything from scratch, and this video will be so long. This is very comprehensive DEX guide, DEX tutorial, so I decided to split it down into two parts. In this part we are going to build smart contracts only, And in the next part we are going to test, I will show you some of the best test cases, you how you can test a DEX smart contract, and how you can build everything from scratch. So just bear with me if initially it will not make sense, because this is not beginner friendly and it will be very complex smart contract tutorial. So it will not make sense initially, so eventually it will make sense. So let's go ahead and let's delete this one as well, and let's create a new file inside this src directory. Let's name it rsk dex.sol, and you can see here our OpenZeppelin contracts library version 5.3.0 has been installed. And let's set up our remappings to avoid some red lines from the our VS Code editor. So to set remappings, you can run this command forge remappings.txt, and you can see our Foundry automatically generated the remappings by setting our remappings. So we are good to go. Let's pull it down, and let's start writing the smart contract. So let's start Pragma license MIT, license identifier MIT, and we are going to use 0.8.20 version. And let's go ahead and let's make it our contract rsk dex is ownable and not and actually yeah, since we installed the OpenZeppelin, let's import the libraries. We will need IERC20 library, safe ERC20, ownable, and for security, reentrancy and math. Let's import one by one. Import, let's first import IERC20 from, by the way, this is the named import we are going to use, and this is the best. Let's say token slash ERC20. I get IERC20.sol. This is the right. Let's import safe ERC, import safe ERC20, safe ERC20 from slash OpenZeppelin contracts slash token slash ERC20 slash I guess utils and safe ERC20.sol. That's it. We also going to import ownable. Thanks to Copilot, we need to import reentrancy guard, I do spelling mistake, from OpenZeppelin contract slash I think utils slash reentrancy guard.sol. That's it. And the important math. So most important, the math from OpenZeppelin contracts slash utils, utils slash math and math.sol. That's it. And now let's make it reentrancy for security. Let's make it ownable and reentrancy guard. And let's first declare, I think there is something, safe for, it's safe ERC20. Some spelling mistakes. OpenZeppelin contracts token ERC20 utils and safe ERC20. And now let's make it, let's first declare here using safe ERC20 for IERC20, and also we need to declare here using math for uint 256, and let's format the documents. What it is saying, identifier not found or unique. We did again some spelling mistake, and it will still throw an error because we didn't set the constructor here. So let's set first constructor, and let's make it ownable, and inside the ownable it is taking the one parameter as the address. So let's do this and it will go away. Identifier not found. Yeah, so we are good to go. We declare the safe ERC for IERC20. I hope you have basic understanding of Solidity smart contracts. So let's go ahead and let's declare the layout of our smart contract. So we will have events here. So let's go ahead and not Netscape. It will be, let's declare like this, events. Also we will need the structure, and not like this. We will also need the state variables. I got state variables. We will need, let's say, public and external functions, and we will also need internal functions. Internal functions. Let's see, there we go. Now let's first, I think, declare the structure of our, we are going to create a pool. So let's declare the first structure of our pool first. So for that, let's create a struct and let's name it pool. And how we declare? So inside that, let's copy the IERC20, and we will need the token A and IERC20 token B. Just bear with me, I will explain you everything. And in 256 reserve A, reserve B, and into 256 total supply. Also we will need reserve, we will need to do reserve 0 multiply reserve 1 as an immediately after the most recent liquidity event. So for that, let's declare u int 256. Let's name it last, and we need to declare the mapping here as well. So let's declare the mapping. We will map address to int 256, and let's name it liquidity. That's it. There we go, our structure is ready. Now let's declare here some state variables. So for state variables, we will need some mappings to track pools and to if whether the pool exists or not. So let's declare one by one. Mapping of the, let's declare first for pools, mapping of bytes 32 to the entire pool. We have to, let's map the entire pool of byte 32, and let's make it public, and pools, let's name it pools. Also we need to add another mapping of byte 32 to, now this time we need to make it bool, whether pool exists or not. So let's make it public and let's name it pool exist. And now let's go ahead and declare some constant variables for phi denominator and phi numerator. So let's go ahead and do this one by one. Int 256 public constant, and let's name it phi denominator, and let's say 1000. So by the way, this is how you this is the best practice to declare the constant variables, so other smart contract engineers can read your code, other auditors, security researchers can read your code. So there are no protocols, but this is the good practice. As a smart contract engineer, you have to make it all the or the words the capital. So let's go ahead and declare another uint 256 public constant key numerator, let's say 3 for 0.3%. I hope you have understanding of how numbers works in Solidity. And now let's declare another to uint 256 public constant minimum liquidity, not 1000 here, let's say in to multiply 3. There we go. What's the wrong here? Expected primary, I think this is my VS code here. And now let's declare for price oracles. Let's declare the mapping of bytes 32 to uint 256. Let's make it public and price 0, cumulative last let's declare another mapping. I made it public. It's 32 cumulative 1 last, thanks to copilot. And for the block dot timestamp block timestamp last, not block dot, mapping of the bytes 32 to int 256 public block timestamp last. So I think, yeah, let's not make it uint 256, let's make it uint 32. You will understand very soon why we making this uint 32. We are following some of the gas optimization practices. So we done with our we imported the libraries from Open Zeppelin. We declare the safe ERC to IARC20. We declare the struct and the state variables and price oracles as well. So let's create functions here. So we will need some public external functions and internal function. I think it's a good way to start with external functions, internal functions first. So it will not make sense initially for you, maybe, and I hope you have understanding of what are the internal external functions, because we will Why we are starting with external function first, sorry, internal function first? Because we will going to call the internal functions inside the public and external function. So let's start with first internal functions. For that, I'm not going to explain you what are the internal functions, and things will not make initially. Just bear with me, and you will be understand everything very soon. So just follow with me, follow along with me, follow the tutorial, the line by line, and also if you stuck anywhere, I'm going to give you entire GitHub repository of this project. So don't worry, you can always go back and check out the code. So let's go ahead and let's add the first internal function here for the add liquidity. So let's declare the add liquidity, and since we are adding liquidity, this is our internal function. So let's make it internal, and view returns what it will return. It will return the amount A and amount B thanks to copilot. Also, it is going to take five parameters. One is for the pool, and let's make it inside the storage. Let's make it pool. I think I made the spelling mistake here, and there we go. What's wrong? This is just VS Code error. Yeah, and amount A desired. So amount should be in uint. Amount A desired. Amount uint 256. Amount B desired. Amount A amount. Let's copy and let's make it B. Amount B desired. And also we will need to make it amount A min and amount B min. So these are the parameters we are taking here. And let's format, let's go ahead and let's write the functions body. So let's add here the if else condition first. If pool dot reserve A is equal to 0 and pool dot is equal to 0, inside that let's add some complex logic. Amount A and the amount thanks to copilot is equal to amount A desired and amount B desired. Now let's add here else condition, and inside the else condition let's declare uint 256. Amount B, let's add amount B optimal is equal to optimal, I think, yeah, is equal to, let's say, amount A desired, and let's multiply this. This is the mathematical operation we are doing here. So just bear with me, things will not make sense. So it will make sense, just bear with me and just follow along with me. So amount A desired, and we need to multiply this for to pool dot reserve B, and let's modulo pool dot reserve A, and that's it. There we go. And inside that else we need to add another if condition here. If amount be optimal, now we declare this variable. If amount be optimal is less than or is equal to amount be desired, then we have to do this task. What's wrong? The primary expression. Now let's add the condition here, require amount be optimal is greater than or is equal to amount be min. Let's copy this from here and paste here, amount be min, otherwise we will throw an error here, insufficient be amount, insufficient be amount. And in, let's go ahead and let's declare amount A, I think, yeah, amount A, and amount B is equal to amount A desired and amount B optimal. That's it. Now inside that we need to pass another, inside we just follow along with me, we have if condition and if else, and inside that else we have again else, if else condition. So just follow this. So inside the else, let's declare here another local variable, let's say u into 256 amount a optimal, a optimal, and let's initialize this with amount b desired. Let's copy amount b desired from here, amount b desired, and let's multiply this full dot reserve thanks to copilot, and full dot reserve full dot reserve. That's it. There we go. Now let's assert this, assert, and the condition is amount a optimal is less than or is equal to amount a desired, sorry, yeah, I think, yeah, amount a desired. And now if let's add here another condition, the require amount a optimal. Let's copy this here from here, amount a optimal it should be greater than or is equal to amount a min, amount a min, and if it is not like this, then we need to revert insufficient in a amount. And now let's go ahead and amount a, amount b is equal to amount a optimal and amount b desired. So this is the very comprehensive and long, very long function we added here. So you can see here, and we are following the best smart contract development practice, which is the, when you are working with professional smart contract, you have to follow some protocols, so such as CEI, check effect interaction. So we are doing this only. So this video will be so long, so again I decided to split it down into 2 or 3 parts. So I think in this part we are going to build internal functions only, because this video will be so long, and in the next part we are going to build the entire, we will going to complete the entire smart contract. Let's go ahead and let's create another function with another internal function, which is the function mint. Let's start. Let's make it internal, and also it will return and liquidity, internal returns liquidity. I think liquidity, what with liquidity, it should liquidity. Yeah, we forget to add the type here, so let's make it UNT 256. And now the mint function will take the same parameters, so let's copy this from here, go ahead, but it will not take 5 parameters, it will take only 2 parameters, the address of the two, and let's go ahead and let's start writing our another internal function here. So this will be again very comprehensive function, so just stay focused. Let's declare some local variables first here. So first you into 56 for the balance A. Balance A is equal to pull dot token A dot balance uh, of this is the special function in Solidity, and address this, and the balance B you int 256 balance B it's equal to pull dot balance is equal to address this, and the same amount. Let's first declare the this one is equal to amount a amount A is equal to balance A minus pull dot reserve A, and amount B int 256 amount B is equal to balance B minus pull dot reserve B. Now let's go ahead and add the if else condition here first. If pull dot total supply is equal to direct equal to 0, then we need to add here the logic of liquidity is equal to math dot sqt. When you are working with DEX smart contracts, you need to use this. So remember, now we need to multiply amount A to amount B. So Copilot already suggesting us we also need to minus minimum liquidity from here, and now let's add here pull dot total supply, and in from that total supply is equal to we need to add here the minimum liquidity. So let's copy this from here and add this here minimum liquidity. Now what we have to do, we need to add the else condition here. Liquidity is equal to, we need to add, we need to call this math dot min function, and inside that min we need to pass amount A multiply pull dot total supply, and from here to pull dot reserve A. That's it. And the same here, amount B multiply pull dot total supply and reserve B. And that's it. let's go ahead. What is the wrong here? Linter is undefined. Yeah, we need to add we forgot to add this here. And now let's add the condition here. The required condition, liquidity should be, oh my bad, liquidity should be greater than 0, otherwise we will revert an error, insufficient liquidity minted. There we go. And now let's add pull dot liquidity. We declare the mapping that 2 plus equal to liquidity, and pull dot total supply plus is equal to liquidity. Now again pull dot reserve A is equal to balance A. Let's copy this from here, paste it here, balance A, and the pull dot reserve A, balance B, and that's it. There we go. What is the error here? I think this is just VS Code error and it will go away. So that's it. We declared the two functions here so far. We built two internal functions, and we will continue to build. This will be comprehensive tutorial. So in this tutorial we only going to declare the build internal functions, and we will continue to, in the next part we will continue to complete the entire smart contract. So just bear with me, we will write two more functions, and I will not make bore you, it will be very long video tutorial. So just bear with me, and we will add one more internal function, which is burn function, and after that we will declare the update function, and in the next part we will use these internal functions into our external and public functions. So it will be very convenient for us to for you to understand, and for you to uh, make sense. So let's go ahead and let's declare here the burn function burn, and the burn function will take a parameter of same as mint. The first, just go ahead, and the tick is 1, and also liquidity u into 256 liquidity. Let's build here, and address of the two, and let's make it internal, and make it will returns what it will return. I guess you have understanding of what it will return. So it will return right amount A and amount B. Now let's go ahead and let's first add the condition here. So let's require this, and pull dot liquidity, and inside that we need to pass, I think we pull dot liquidity, and inside that we need to pass the message dot sender, who is the caller, should be greater than or is equal to liquidity, otherwise we will revert an error, insufficient liquidity. What is the expected primary action? This is just VS Code error, so don't make it. Let's go ahead and now let's declare the some local variables. Let's go uint 256 balance A is equal to pull dot token A token A token A dot balance of and address this thanks to copilot, and balance B pull dot token B dot balance of address dot this. Let's go ahead and now initialize the amount A is equal to liquidity. We need to multiply this liquidity to balance A. So amount A is equal to liquidity multiply balance A. Balance, copy this from here and balance A and do this pull dot total supply. There we go. Now amount B or amount B is equal to liquidity multiply balance B and pull dot total supply. And now we need to add the condition here, which is the amount A should be greater than 0 and amount B should be greater than 0, or we will revert an error insufficient liquidity. Let's say burn. Let's make it clear. We are burning this and we will add the burn function. This is just internal functions we are going we will use this internal function inside our main function, so just bear with me. And now after adding this condition, let's add our further logic. Pull dot token A, I think not token A, pull dot liquidity, and inside the liquidity remember we added the state variable of mapping. Inside that we need to pass message dot sender and let's minus is equal to liquidity. There we go. And now pull dot total supply minus is equal to, let's copy this from here, liquidity. Let's go ahead and let's make it pull dot token A dot safe transfer. This is the special function we gonna use from the Solidity to amount A. We need to pass token B safe transfer to amount B. Let's go ahead and let's wrap this up by pull dot reserve A is equal to pull dot token A dot balance of and address this and address pull dot reserve B pull dot tokens balance of address this, and we're done with this function, this internal functions as well. So you can see here inside this function, inside this burn functions, we take three parameters: the full storage full, and we made it internal. We add the first condition here. After that we declare the some local variables and we add another condition and we set our logic. And this is again the last function of this part we are going to add, which is for the update. For updation, let's create another function. Let's name it update. I some of you have question why I am starting this internal functions with this underscore. This is just best practice. You have to make the internal functions uh, to start with underscore. So let's go ahead and create this one. Let's make it update the full, and our full id should be in bytes hexadecimal format. So this get this one bytes 32, and full id will take a parameter. Let's make it internal, and now let's directly, it will not return anything. So let's directly declare the local variables int256 and block timestamp block, yeah, block timestamp is equal to int 32, and inside that we are going to pass block dot timestamp and modulo to multiply 32. And let's go ahead and let's add another variable here uint32 time elapsed. Let's name it time elapsed is equal to block timestamp minus block timestamp last. Remember, we declare the mapping above in our state variables. I will show you the block timestamp last. So this is how we designed our smart contract. Block timestamp, and inside that we have to pass this full id, right? I think we did something. Not time 32. Let's, I think let's make it uint 256, or what we did here. Type uint is not implicitly converted, expected type u32, and there is gone. There we go. Now let's add the if else condition here. So if time elapsed is less than 0 and full dot resolve a is not directly equal to 0, and full dot resolve b it's not directly equal to 0, we did some syntax error here, and there is gone. Now we need to pass price 0 cumulative last. Inside that we need to pass the full id, and we need to make it plus equal to uint 256, and inside that we need to pass full dot reserve b multiply a single multiply 2 double my 112. This is the formula, and we need to pass full dot reserve a. Now let's multiply this with time elapsed. There we go, time elapsed. And now inside uh, below this, let's price one cumulative last, and inside that pool id, let's pass pool id and let's make it plus equal to uint 256, and let's make it pool dot reserve a. Let's multiply this 2 and 112. Let's divided this with pool dot reserve b and multiply time elapsed. Let's copy this from here, and there we go. And what are the four errors we have here? The These are not errors, these are just there we go. And these are not error, these are just warnings. And let's go outside the if else conditions, and let's block timestamp last. Inside that pass pool id is equal to block timestamp last, block timestamp, and that's it. Let's what is this warning? Can be restricted to view. Let's make it view. For now it will not, we will not need to make it view. And what is this? Unused local variable, time elapsed. These are the warnings, it will go away, so don't worry. And that's it for this part. So far what we have done in this part, we initialize the Foundry project. Just quick recap of this part. Our phenomenal DEX tutorial, we are implementing the exact the somehow same implementation, same formulas, using the same formulas or like latest Uniswap v4. So we initialized the Foundry project, we installed OpenZeppelin smart contract libraries, we imported these functionalities, we declare the contract, we declare the math and say PRC, we declare the structure of our pool and the state variables, and we declare the internal functions. The first internal functions, we declare the add liquidity, where we take 5 parameters and added some logic. We declare the another internal function mint, and we declare another burn function, one internal function, and the update internal function. So let's try compiling this by running. If anything error, it will yeah, it is, the error is equal to 132. Where is 132? Yeah, it should be, I think there are three, it should be not this. Now let's declare, and there we go. We have block timestamp 138, block timestamp you into not implicitly convertible block timestamp. Yeah, we need to make it, I think, uint 32. And now let's compile block timestamp uint. We need to make it what uint 32, I guess uint 32. There we go. And now let's, yeah, you can see the compiler successful, and our smart contract is compiling. So that's it for this part, and I will see you in the next part, where we will complete and we will finish our smart contract. Bye bye, and I will see you in next one.